Okay, so Assalamu alaikum everyone, and welcome to, I think, part 4 of trigonometry. Okay, in this part, we will be covering harmonic trigonometric identities, and then we will only be left with, I think, graphs. Yeah, I will do a separate video of graphs, and after that, of course, we need a lot of practice, and then we are good to go. So before we cover harmonic trigonometric identities in this video, I would like to go through certain values which I think one we should remember for the exams because they turn out to be pretty useful, right? So let's just make a table of certain values of sine, cos, and tan, which you should remember. All right. So let me just make a rough table here. Sine theta, cos theta, and tan theta. All right. And let's say 0 degree, 30 degree, 45 degrees, 60 degrees, and 90 degrees as well. Wait a minute. Yeah, okay. And if we write the same values in radians, that would be 0 is 0, and this is pi upon 6 in radians, and this is 45 is pi upon 4, and 60 is pi upon 3, and 90 is pi upon 2. So the values I would be writing for sine 0, sine pi upon 6, sine pi over 4, and so on, and cos 0, cos pi upon 6, cos pi over 4, and so on and so forth. And same goes for tan. You will have to remember these values for your exam because they, believe me, turn out to be very useful at times. Okay, so zero is sine 0 is 0. The value of sine 0 is 0, and sine pi upon 6 is 1 upon 2, and sine 45 is under root 2 upon 2, and sine 60 or sine pi upon 3 is under root 3 upon 2, and sine 90 is 1. All right. There's also a derivation, which I think is not necessary for your syllabus. Just learn these values by heart and you will be good to go. Cos 0 is 1, and cos 30 or pi upon 6 is under root 3 upon 2, and cos 45 is under root 2 upon 2, and cos 60 or pi upon 3 is 1 upon 2, and cos 90 or pi upon 2 is 0. Tan 0 is 0, and tan pi upon 6 is under root 3 upon 3, and tan 45 is 1, and tan 60 is under root 3, and tan 90 is infinite. All right, so just copy this table. In fact, copy everything I write it right here, like I said earlier in earlier parts. Okay, so just copy this and learn these by heart. Okay. Now I know you must have been wondering to why can't we just put a calculator here, right? To find these values. But at times, let me just give you an example. Uh, let's say we have 1 here. This is not an actual question. It's uh, I'm just making this up, but it is based on a pretty lengthy exam question. So there was this question in which we had to know that 1 equals 1045 in order to prove an identity, right? So unless you didn't learn this table by heart, you wouldn't know that 1045 is that 1 is 1045, or maybe 1 upon 2 is sine 30, or let's say 1 is also cos 0, or under root 3 upon 2 is cos 30, right? So at times it would be tested, even though it's rare, but it can be tested. So it's it's I would really recommend you to learn this by heart. All right. So yeah, give me 1 minute. Now let's do a couple of questions before we move on to harmonic identities. Let's say we have here cos square pi upon 8 minus sine square pi upon 8. All right. So now we know that there is an identity being applied here. This is cos square theta minus sine square theta, which is cos 2 theta as studied in the earlier videos, right? So let's just put pi upon 8 in place of theta, which is pi upon 8, right? This and this cancels out. You're left with cos pi upon 4, which is under root, if you solve it using a calculator, it is under root 2 upon 2. All right. Now, similarly, this same identity of cos 2 theta can be tested in other ways, right? So let me just show you. Let's say we have 1 minus 2 sine square pi upon 8. This is also cos 2 theta as studied earlier. All right. So what we will do is apply the same identity here, right? Cos 2 pi upon 8. This and this and this is essentially the same thing, all right, as studied earlier in the identities video, all right. So we will just apply cos 2 theta here. We'll write cos 2 theta, okay, which is cos 2 pi upon 8 cos pi upon 4, all right, which is what? Under root 2 upon 2, right? So these examples are just to give you an idea how identities, how you have to think, right? You always have to be mindful of the identities that you have studied, and you always have to consider the possibility that the identity studied must be applying somewhere. So that so in order to be, you know, so you have to be vigilant enough, and of course you have to practice a lot. All right, as much as you practice, uh, the more proficient you would become. Okay, and yeah. Similarly, observe here that uh, this is the question that needs to be solved, and an identity is being applied here. And the identity which we studied here is uh, which is applied. Notice that this is sine theta cos 25 minus cos theta sine 25, which is the same thing as sine A cos B minus cos B sine A, right? Which is we studied, which is sine A minus B. like we studied in the identities video. So what we are going to simply do is write it as sine theta minus 25, which is 1. Now, if you are going to solve it, which is very basic, you are going to get the answer. All right, if the relevant range is given. Okay, this I'm not going to solve it because it's very basic. This was just to give you an idea of how things really work out here. Okay, so without any further ado, I think we should start with harmonic trigonometric identities. Right, this is the second last thing in this chapter, and then obviously you need a lot of practice. I keep on saying that because it is really important, particularly in this chapter. Okay, so the function of trigonometry. The function of trigonometry, or more simply, harmonic trigonometric identities. Right. So let's just write what it is. If a trigonometric function comprising of sine and cos, comprising of sine and cos is such that it can neither be converted into a single function, into a single function, nor can any trigonometric identity, nor can any trigonometric identity, wait a minute, yeah, nor can any trigonometric identity be applied on it. Then we need to apply the function of trigonometry. Then we need to apply the function of trigonometry, or simply the harmonic trigonometric identity. Harmonic trigonometric identity. Right, so if a trigonometric function comprising of sine and cos is such that it can neither be converted into a single function, nor can any trigonometric identity be applied on it, then we need to apply this function of trigonometry, or the harmonic trigonometric identity. So first, let us consider cases in which uh, a trigonometric function can be converted into uh, a single function, right? And then we will consider cases in which it cannot be, and when we need to apply the harmonic function. All right. So let's start off with when we do not need to apply harmonic trigonometric identity. All right. Cases in which cases in which we don't need to apply harmonic, right? Cases in which we don't need to apply harmonic. So first question we have is, Let's say 3 sine x minus 4 cos x is equal to 0. Now notice this can be converted into a single function, right? If we solve this, let's say 3 sine x is equal to 4 cos x, and sine x upon cos x is equal to 4 upon 3. And sine over cos x is what? Tan x. So yeah, and we can solve for tan x then, right? And if we solve for this, we will surely get the answer, right? So in this case, we do not need to apply harmonic trigonometric identities or the function of trigonometry because it can be solved without it. Let's just solve it as well. Tan x is 43, and also the range lies between 0 and 360. Okay, and tan inverse is 4 upon 3, and we have 53.1 degrees. All right, so tan is positive in first quadrant and the third quadrant. 53.1, 53.1. So we have angle of 53.1 and 233.1 degrees. X is of this. Okay. So yeah, in this case, we did not need to apply harmonic because as we studied, this function is such that it can be converted into a single function. So let's just look at two more cases in which we do not need to apply harmonic identities, and then we will study when we do need to apply harmonic identities. Okay, so we have, let's say, 3 sine square x minus 4 cos x is equal to 0. All right, now notice that sine square x can be converted. It's the same as the sine square x plus cos square x is equal to 1. We know this identity. And sine square x is 1 minus cos square x, right? So we can just write it here. 1 minus cos square x minus 4 cos x is equal to 0. 3 plus minus minus 3 cos square x minus 4 cos x is equal to 0. And if we shift everything there, we get 3 cos square x, right? Plus 4 cos x minus 3 plus 4 cos x minus 3 is equal to 0. Notice that this turns out to be a what? Yes, a quadratic equation. So we are simply going to solve this quadratic equation, and we will get, I'm not solving it, but you will surely have to solve it in your exam, okay? Because this is not the concept I'm trying to teach right now. So I'm just going to solve it with the help of calculator, but in the exam, obviously you have to solve it manually. Okay, so if we solve this, we get two values, which are this value will be rejected, and we will get, and then the cos axis 0.535, right? And the basic angle would be cos inverse of 0.535 will be 57.65 degrees, 66 rather. All right. And then we know that cos is positive in first quadrant and in the last quadrant. So x be uh would lie here and here, 57.66 degrees, and 360 minus 57.6 gives us 302.34 degrees. All right. So yes, in this case, we did not have to apply harmonic, right? And one more thing which I believe it's important here is that in exam, unless otherwise stated, you have to always round off to one decimal place. Angles have to be rounded off to one decimal place unless otherwise stated. All right. So this would be 57.7 and 302.3 degrees. Unless the question says specifically to round it off to, second or third, you always have to round it off to first decimal place. Okay. Now let's study. Now let's study the function of trigonometric identity or the harmonic. These were cases when you did not need to apply harmonic. Okay, so the function of trigonometry or the harmonic trigonometric identities. So let's say we have a sine x plus b cos x that could not be converted into a single function. So that would be r sine x plus alpha. Okay, and let's say we have a sine x minus b cos x, that would be r sine x minus alpha. Similarly, a cos x plus b sine x would be r sine r cos r cos a cos x plus b sine x is r cos x minus alpha, right? And a cos x minus b sine x is r cos x x plus alpha. Okay, where 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 r is under root of a square plus b square, a square plus b square. And notice we are going to ignore the sign, right? So whenever we need to calculate the value of r, we are going to ignore the signs, just under root a square plus b square. And alpha is tan inverse b upon a. All right. Let me just write that note here as well. The signs of a and b, the signs of A and B are to be ignored, are to be ignored because alpha will always, always be acute. Okay, so this is something you need to remember by heart. All right, and in fact, most of the time, it's the question usually asks you to convert this into this form first, and then you have to solve it further. But if in case it does not ask you, and I think, yeah, if in case it does not ask you, then you surely have to remember this, right? Because let's say you encounter a question in which a sin x plus b cos x cannot be converted into a single function or cannot be solved, right? So you need to know that a sin x plus b cos x is r sin x plus alpha. And similarly, a sin x minus b cos x is r sin x minus alpha, and so on and so forth, like the examples we like the ones written here, right? So let's just do a couple of questions to exactly get the idea, right? So yeah, these cases which we studied in this could be converted into a single function, right? Or could have been solved further. Now the examples we are going to be looking at uh, now onwards, in those examples, this cannot be converted once into a single function. That's why we need the function of trigonometry or the harmonic trigonometric identities. That's why we need to apply this. Okay, so let's just start with our very first example. Okay, so let's say we have 3 sine x minus 4 cos x is equal to 5. All right. Now notice in this example, this cannot be solved further, right? So we need to apply the harmonic identities. This is a sin x minus b cos x, right? So what is a sin x minus b cos x? We studied a sin x minus b cos x is r sin x minus alpha. So this is r sin x minus alpha is equal to 5. So we'll just calculate the value of r, which is under root a square plus b square. All right, which is what? Which is under root of 25, and this is 5. So we have r, and now we also need to calculate alpha. Alpha is tan inverse 4 upon 3 b upon a. We know we ignore the signs, and alpha is 53.1 degrees. All right. So we have r and we have alpha. So we are just going to write it as 5 sine x minus alpha, which is 53.1. All right. Which is what? Which is 5. Sine x minus 53.1 is 5 upon 5, which is 1. So we have sine x minus 53.1, which now can be solved. All right. So we need to find the basic angle. And since sine is equal to 1, now we'll do all the ordinary steps, right? Sine is 1. We need to draw a graph here. All right. So this is what a sine graph looks like. 1 and 90. So notice x minus 53.1 degree is what? Is 90. Sine 1 is 90. 90. So x is minus 53.1 plus 53.1. X is 143.1 degrees. All right. So another example. Let's say we have 6 sine x, 6 sine x plus 8 cos x is equal to 5, right? So this again cannot be converted into a single function, or it cannot be solved further without introducing harmonic trigonometric identities. So notice that 6 sine x, a sine x plus b cos x is what? A sine x plus b cos x is r sine x plus alpha. All right. This is r sine x plus alpha is equal to 5. All right. So we need to calculate the value of r. R is under root a square plus b square. Under root a square plus b square is 10. All right. And similarly, what is alpha? Alpha is tan inverse b upon a. B upon a. Alpha is, if we solve it, we will get 53.1 degrees. All right. So tan and alpha. Right? So r tan, wait, tan sine x plus 53.1 is 5, which means sine x plus 53.1 is 5 upon 10 or 1 upon 2. Sine x plus 53.1 is 1 upon 2. All right. So one more thing. Let's just say range here is 0 till 360. All right. So now we are going to do the usual steps. We are going to alter the range, right? X plus 53.1, 53.1, and 360 plus 53.1 is what? Is 413.1. So this is the new range. Okay. Now we are going to solve for, we're going to find the basic angle. The basic angle is sine inverse 1 upon 2, which is 30 degrees. All right. So a, let me just draw it with a different color because it seems good. Yeah. ASTC, and we know sine is positive in the first quadrant. What happened to my marker? Wait a minute. Wait a minute, guys. Oh yeah, sorry for that. My screen got hanged. And yes, so yeah. Where were we? Yeah, we were discussing that. Yeah, since sine lies in the first quadrant, sine lies in the first quadrant and the second quadrant, right? So here it is 30 and here 30. All right. So sine is uh, x plus 53.1 is plus 53.1 degree is 30 and 180 minus 30, which is 150 degrees, right? But since the range is from 53.1 till 430.1, we'll also add 360 to 30. 30 plus 360 is what? Is 390. But if we add 150 to 360 to 150, it gives us a value which is greater than this range, right? Which is outside of this range. So now we are going to simply solve for this. X is 30 minus 53.1, which is minus 23.1 degrees. And by the way, yeah. One thing, this value is outside of our range, so we are going to reject it, right? And these two values are only within our range, as you can see it, right? So yes, so now we're going to solve for it. X is 150 minus 53.1, which is 96.9 degree, and 390 minus 53.1, which is 336.9 degrees. All right, this is our answer. Okay, so yes, today we studied harmonic trigonometric identities in part 4 of trigonometry. I hope everything so far is good and you are practicing a lot, because practice is literally everything in this chapter. Even though I tried my best to teach you all the concepts, but if you won't practice enough, you are not going to get it. There's no simply there's no escaping practice. Uh, so yeah, in the next video, part 5 of trigonometry, we are going to study trigonometric graphs, and then in part 6 possibly, inshallah, I will also be coming up with part 6, in which we are going to do a lot of past paper questions, real exam like questions, to uh, actually understand what the questions are like, right? So that's it for today. Take care. Allah Hafiz.